Thank you guys so much for joining us today to talk about the Windows Registry. It turns out there is always something new. So my name is Kim Stone. I am a director in the software development group at Strauss Friedberg, which is part of Aon. So I've been in the DFIR development space for over 20 years, and I love the fact that it's a constantly expanding field, meaning people just keep doing things they shouldn't with computers.
My name is Shane McCulley. I'm a senior developer with Strauss's development group. I have a master's in computer science with a focus in cybersecurity from the University of New Orleans. I worked with Dr. Vasyl Rusev, researching cloud forensics there, and I've been doing forensics tool development ever since.
So Strauss's mission is to seek truth, and our dev team is devoted to making our DFIR team as effective as possible. So they help clients investigate cyber incidents, ranging from email compromises to nation state attacks. And they also work alongside our other practices, such as security advisory, pen testing, and threat intel to provide our clients a holistic view of cybersecurity. So today we are going to talk about two things. So first, we're going to introduce Nataken, Strauss's open source registry parser. Next, we're going to talk about shellbags. So not everything about shellbags, that could basically be a whole training course itself, but we will cover how shellbag existence doesn't mean that a folder was opened. We'll show you a more reliable method of determining if it was opened, and then we'll use that approach to improve timeline analysis. Finally, we'll wrap things up. So it's 1992. Batman Returns is the #1 movie in the US. Boyz II Men is topping the charts. 2G mobile phones are introduced. And Windows 3.1 is released. So while Windows 95 really leaned into using the registry, 3.1 was the version that introduced it. So is there really anything new to discuss about an operating system file that has been around over 30 years? Yes. So as you know, these days the registry stores a ton of information about the system, users, and applications, and it is a key source of forensic goodness. So what is new? The registry files actually themselves have some underused information to offer up, and then there is the matter of properly interpreting the artifact data within. So what is Nataken? Nataken is another name for the enzyme glucose oxidase. Glucose oxidase catalyzes the oxidation of glucose to hydrogen peroxide. Honeybees generate this enzyme for their honey, where it acts as a natural preservative. So Nataken helps preserve things in hives. Nataken is also Strauss's open source registry parsing project, and that is the one we are talking about today. So why did we reinvent this wheel? There are very solid existing solutions out there, and most of them ticked some of the boxes we were looking for, but not all. So what are these requirements? We needed something powerful, flexible, fast, cross-platform, and open source. So we will explore each of these and see how Nataken achieves them. So is Nataken powerful? Yes. It supports transaction logs, not only applying them, but analyzing them, and we will dig into this more in a few. Nataken can also recover data in multiple ways. And finally, Nataken can return file offset information for every field of every key and value that it parses. You can always go back to verify exactly where the results are coming from. I also want to note that we've run Nataken on over 240,000 hives from over 10,000 real-world systems. So part of being powerful is being stable and well-tested, and our tool checks this box as well. Along with the library, I apologize, these slides got a little lost in translation somewhere along the way. But along with the library, Nataken includes two command line utilities that are ready for you to use, regdump and regcompare. So is Nataken flexible? Yes. It's written in Rust and can be used directly in another Rust program or in Python with the accompanying Python bindings. You can iterate through the entire hive, or you can target only specific keys with full paths or regular expressions. And finally, both of the bundled utilities have various outputs which are tailored to different use cases. So is it fast? Yes. As mentioned a moment ago, it's written in Rust. And if you like C++, you will be incredibly frustrated by Rust. But it is fast like C++, it has a modern toolchain, and the language design itself does prevent subtle bugs that can plague even experienced developers in other systems programming languages. So there are two main camps of forensic registry parsers. There's those written in Python and everything else. So we ran some performance comparisons using a small ntuser.dat file along with a pretty large software hive. So prior to writing Nataken, we used Willie Balanton's Python registry library. It was very solid and served our products well for many years. But we swapped it out for PyNotaten, Nataken's Python bindings. And as we see from the comparisons, they show that having the heavy lifting of registry parsing in Rust does make PyNotaten quite a bit faster. But really comparing like a lightweight Python wrapper around a Rust program to a pure Python implementation is not really playing fair. So let's look at something compiled. RACMD is the command line complement to Eric Zimmerman's Registry Explorer, and it's written in C#. So running the tools with similar settings, we see that Nataken turns out to be faster there as well. So if you are a Python programmer who is familiar with Python registry, using PyNotaten instead should be a pretty easy swap. And if you are jumping on the Rust train, then using Nataken will make your processing fly. So finally, the quickies. We needed something that was cross-platform because in our environments, we support Windows, Linux, and macOS users. And hey, since we made this, we, with the blessing of myriad corporate lawyers, got to pick a permissive open source license. We benefit a lot from open source, and we look for ways to make contributions back. Mentioned before, the Straws motto is to seek truth, and we want Nataken to benefit from peer review and community testing to make sure we are meeting that goal. So let's talk about these Nataken utilities. RegCompare compares two particular registries or two matching folder trees. It can be used for comparing the state of a system to a known good state, such as from a gold build image. It's also really useful for testing. So for instance, if you want to see the effect of a particular action upon the registry, you can really easily compare exported hives from before and after and see what changed. So by default, the output is a text format similar to what RegShot, a live registry comparison tool, provides. So this is an example of that output from before and after CCleaner was run. Lots of deletions as we would expect. And you can also choose to format the data in a unified diff format like a patch. So I particularly like looking at this output in BeyondCompare's patch viewer. And if you're not familiar with it, quick plug, there's a lot of file comparison viewers out there, but BeyondCompare is pretty great. There's a ton of different viewers. It's very easy to swap the type of comparison viewer you're using. And in particular, it has this patch viewer, which displays a single diff file as if it were two files for side-by-side comparison. So next up, log analysis. Let's lay a little groundwork. What are these log files? Windows uses these log files, often referred to as transaction log files, to optimize performance and ensure stability of a primary Hive file. That primary registry can be parsed on its own just fine. That consistency is part of the design, but it just means that it might be slightly old news. If the registry is dirty, meaning it's out of date, then applying these log files may be required in order to have a parsed registry which accurately reflects the state of the system that it came from. So the formats of both the primary registry and the log files is pretty straightforward and really rather similar. So the primary registry file has a header and a series of Hive bins. Each of those Hive bins contains cells, and one cell contains a particular record. This could be a key, a value, security information, or other structural data. The log file has a header and a series of log entries. Each log entry contains a series of updates and dirty pages, and each of these is simply a file offset into the primary file, a size, and then the bytes that should be applied on top of the primary file at that offset. So most forensic registry parsers support log files, meaning that they'll apply the relevant entries in the log files to bring the registry to the most updated state. But there's potential information stored in between the starting point and that fully updated registry. These are prior states of keys and values that Nataken can capture. So this is not a novel idea. Maxim Shuanov wrote a blog about it back in 2018, and his YARP tool can retrieve these records. Other folks have written about it since, but we really don't feel it's gotten the attention it deserves. I mean, being able to see the past is always useful, but especially when faced with threat actors who are trying to work quickly and erase their tracks. So one more note on the structure. What are these red squares? These are important. These represent the sequence numbers. Each log entry, a set of updates to the registry, gets an incremented sequence number. The primary file also has a sequence number that corresponds to these log entries. For Microsoft documentation, the latest log entries are written to the registry at least once an hour in a process called reconciliation. In reconciliation, all unapplied log entries are copied over to the primary file. At that point, though, the sequence number in the primary file, the sequence number is not updated. This means that the log entries have been written to the primary file, but we can't actually tell that just from looking at the files. That primary file sequence number is actually updated in the validation step. Validation happens pretty rarely, like when the Hive is unloaded for shutdown. So for most of the life of the registry, it's in this state where things have been reconciled, they've been written to the primary file, but not validated. So in this case, parsing the registry after each log entry could give us an inconsistent record because we've actually applied an older state over a newer one. But even with this, it bears out that we can still recover valuable info in that situation. So let's take a look at how exactly this works. First, we parse the primary file in its original state. Then we take the first applicable log entry, apply all the dirty pages that are in that log entry, and then parse it again. At that point, we've got two trees of all the keys and values, and we can compare to see if anything's been modified or deleted. Then we do it again for the next log entry, and so on until we've gone through all of those remaining log entries. So now that we know what this analysis is doing, what can you actually get out of it? Last year, some of our team members came to us requesting support for parsing the tray notify icon streams value from the registry. The format's not documented, but we got some sample data and started playing around with it. The first stage was a proof of concept using Nataken. Initially, we just worked with the allocated records, which are noted as current in this screenshot. As you can see, in this case, there's like nothing super interesting in these parsed blobs. So then we also started parsing the recovered records, and this data revealed something more interesting. We see evidence that a portable chocolatey install of AutoHotkey was used to run a script called WinPCAP install. So this kind of gave us the first hint of how powerful transaction log analysis applied across artifacts could be. So how can you start to check out this recovered data? This is where regdump comes in. Regdump, as you might guess, dumps the registry. There are multiple output formats. First up, there's JSON-L. Note it's JSON-L, not JSON, because it's just easier to process line-oriented or record-oriented JSON with other tools versus working with like a single massive nested JSON object. So these objects have all of the data that Nataken collects. It is a lot, but you can use our favorite JSON manipulation method to get to what you want. So next up, we've got XLSX. This is the preferred visual review format. We've kind of carefully considered how to best present all this data so that it's in a flat list, but it's still comprehensible. TSV is the same data that's in the XLSX, but without all the nice formatting. And then finally, there's common, which is a minimal text output for comparing results with other tools. There's two other options I want to call out. First, full field info. This is only applicable to the JSON-L output, and it'll include that file offset info we talked about at the beginning for every field. It is super noisy, and that is why it's optional. Next, we've got recovered only. This is only applicable to the spreadsheet outputs, and what it'll do is it'll filter the results to only include deleted items, modified items, and the current version of any modified items to provide context. So this is different than what you get by just filtering the spreadsheet yourself because of the inclusion of that current version. So how can we use this? Let's talk about timestamps. Registry values don't have timestamps, which is a real bummer for forensics. but registry keys, the folders in a registry, do, and we often rely upon those timestamps to determine action timeframes for the values within. But a malicious actor can modify these timestamps to cover their tracks. Lena Lau of Inverse Cause wrote a blog about this last year, and she observed that there wasn't a great way to tell if this happened. So we followed exactly the reproduction case that Lena outlined in her blog. Using Joachim Schick's set reg time tool, we modified the timestamp of the run registry key. If we take a look at the reg compare output from the registry before and after, we see, yes, the timestamp changed. But what if we only have the after and not the before? This is where regdump steps in. We only have that after version of the registry, but we can see the history of that key very clearly. So back to Mr. Shuanov. He responded to this blog post on Twitter, and he pointed out how the modified timestamps could be recovered using the transaction logs, just as we have demonstrated here. And yet still, this type of analysis doesn't really seem to be a standard part of investigations. We would love for that to change, and we do think making it easier and more accessible could do that. So if you're working an IR case, you're well served by collecting these logs as quickly as you can, because over time, some of what you could have recovered may ultimately be lost. So another interesting case comes from looking at the recovered data after running Shellbag, Analyzer, and Cleaner. We see that log recovery shows us that all of the deleted records are visible, as well as the associated timestamps. But of course, the Shellbag MRU values are just binary blobs. Ultimately, interpreting values like these is outside the scope of the regdump tool itself. But once you have a particular value or a set of values to target, you can enhance them with some code. One approach is to use regdump to filter the output to the key of interest and use that JSON-L output to get to some data you can process further. So let's talk more about that further processing. In order to process registry artifacts accurately, we need to really understand what they're telling us. So with that, I am passing the mic off to Shane, who's going to talk about shellbags and some of the things that they can tell us about user activity on a system.
Thanks, Kim. So shellbags, they've been around forever. It's a quick refresher. They are registry artifacts. They're found in both the int-user and user class hives. They hold window viewing preferences, and they are created not when folders are opened, but when they're interacted with. So exactly when are these shellbags created? It's the first interaction in a shell window, capital S shell window, not a terminal. Some examples include Explorer and file folder dialogues. And on different versions of Windows, different interactions will create shellbags. Some examples of those are creating, renaming, moving. But out of all of these interactions, there's only one that involves opening a folder. So that means the existence of a shellbag does not imply that the folder was explicitly opened. This isn't anything new. It's been talked about for a while. It was noted in a 2017 update to Dan Palega's blog post, Shellbag Forensics, addressing a misconception. So let's take a look at what the structure looks like. Here we have a couple of registry keys, bag MRU and bags. These are our keys of interest. Bag MRU has a tree-like structure, which maps to a location, and bags is a flat structure, which holds viewing preferences. So let's see what it looks like when a shellbag is created. We have the registry editor here on the right. On the left, we will create a folder. If the video starts playing, hopefully it will soon. PowerPoint seems to not be too happy with our slides today. So we'll create a folder, name it Sans. And after we open and close the folder, we'll expect to see a new entry in the registry editor. So here we are, we're closing the folder. We'll update registry editor. And there's our new key, number 1, which corresponds to this Sans folder on the desktop. So as we mentioned, this tree maps to a location. So on the right, we have an example of Eric Zimmerman's Shellbags Explorer, which shows us how this folder maps to last test. This is path specific. So in this case, it was accessed through C users. If you access it through quick access or my computer, it would create an entirely different tree in different shell bags, meaning you can have multiple shell bags that point to the same location. Let's drill into the last test and see what a bag MRU key actually looks like. So this is the last test folder. These 3 numbered values correspond to the 3 numbered subkeys, which are the 3 children that have been interacted with of last test. The binary data contains values that we can parse for the folder path and other properties. You could have a whole talk on the different kinds here and what you can get out of it. Next is the MRU list, telling us the order which these were recently accessed in. Number 2 being the most recently used, followed by 1, and then 0. Finally, we have a note slot. This is our mapping into the other key we talked about, shell bags, where the preferences are stored. So let's take a look at what a preferences key looks like for note slot 86. On the left, we have a couple of different access methods here. We have a dialog box and a shell access. Those are creating 2 different subkeys. We have some UUID keys under that. That corresponds to the folder type. From the dialog box, this is the documents type, and under shell, that is a video optimized type. And on the right, we have some sorting and viewing preferences. So how do these preference keys get created? So we have a video here, a folder on the right. We haven't opened this with cheese folder yet. We've only interacted with it. And it appears that our videos have upset the PowerPoint gods thoroughly so that we have to wait for it to load. So we're going to refresh the registry to make sure that it's up to date with the latest changes. The highlighted key number 19 corresponds to the with cheese folder. We see we have a shell subkey and there are no preferences underneath. It does have a generic value here that tells us what folder type the preferences should be created with. After opening the folder, we'll have a default set of preferences that are created. These are not written to the registry yet. If we refresh, we won't see any updates. They could change before the folder is closed, but at the time that it's closed, it will write those preferences. And we'll expect to see a new key under shell starting with 5C4, which is the UUID for a generic folder type. And that's what we see here with our set of preferences inside. So what are some takeaways that we can see from this? First, the existence doesn't necessarily mean that the folder was open. There's many ways to create shell bags without actually opening a folder. We found that opening and closing a folder creates a preferences key, and we did not find another way to have one of these keys being created without opening and closing it during testing. So that means the preference key existence in Shellbag implies that the folder was opened. So now that we have a clear picture of what shellbags can tell us about user behavior, let's see how we can use that to tell when that behavior occurred. So what can we get from timestamps? As we mentioned before, registry values do not have timestamps. It would be really nice if they did. We can get them from the keys, which are updated when any values are created or updated. So by itself, it's not directly helpful, but we do have the MRU list, which we can use to associate the last written timestamp with the folder that it was updated with. There are a couple of caveats here. This is we call this the last known interactive time, because in this example, folder number 2 could have been visited after that update, and then it wouldn't have been, no changes would have been made to the MRU list or any of the other values, so the last written key would not have changed. And there's a further caveat in that if the parent is the bag MRU key itself, there are some additional considerations there when doing the last known interacted. So we have some timestamps. We can use a decision tree to generate some access windows. Access window, we only had one time. We can also infer the first interacted as long as there are no subkeys, as well as the last known interacted. It's fairly simple. We just have a couple of questions here. If it has no subkeys, we know that the key time is the first interacted. And if it's first in the MRU list, parent's key time is the last known interacted. We'll go through a quick example to see how that works out. At the top, we have reg dump output with a couple of keys and values. We're going to fill in this table starting with the 210 key. We see that it has two subkeys, and so the first interactive time is unknown. We'll check the parent's MRU list. It is first in the list, so we do know the last known interacted for that key. Going to the next one, it has no subkeys, so we know that the key time is the first interacted. This is because there are only two values here, node slot, which never changes, and the MRU list, which hasn't been updated, and it will never be updated as long as there are no subkeys. Looking at the MRU, it is not first in the parent's MRU, it's in the middle, and so we don't know the last known interactive time here. And finally, for the last key, we repeat the same process. There are no subkeys, so we have a first interacted, and we check the parent's MRU, and it is first, so we have a last known interacted. So now that we have some shellbags and we have some access windows, what can we do with them? Let's go through a quick scenario. So we have Mr. Pasta and Mr. Burger, two restaurant rivals. Mr. Pasta sees an unattended laptop at lunch and wants to steal the secret recipes. And let's see what shellbags can tell us about this scenario. So before we start the scenario, we have the preferences key here for the folder of interest that contains the secret recipes. We will save this so we can get a clear picture of what happened before and after the scenario. So Mr. Pasta sees the unattended laptop, runs across the street quickly, plugs in his USB device, and starts looking for the secret recipes. Thankfully, it's on the quick access, and right there is the secret recipes folder. We don't want to copy all of these things though, so let's change the type and only select the recipes so we can filter out those pictures. We'll copy this and send it to the USB device. And we have to work quickly because we don't know when someone is going to come back. So we'll look for some more recipes, and he hears someone coming and he has to quickly eject the device and close the window, thinking that he has left no trace that he's ever been there. But we know that the registry tells a different story. So we'll look at the preferences key. After this, we can use reg compare to see exactly what changed before and after. When we look at these, we see that the sorting key did change as we expected, which caused a change in the last modified time of the preferences key to the time in question, showing that there was activity at that time. So what can we do with a bunch of times? We can timeline it. So we'll collect the timestamps, we'll generate a timeline, and we'll profit using TimeSketch. TimeSketch is an open source tool for collaborative forensics timeline analysis. We have a bunch of events inserted here at the top. We can see the distribution during the time. Each event has to have 3 fields that are required, the date, time. It has to have a message. In our case, it's just the path for the shellbag, and a timestamp description, which is a first interacted or last known interacted time. And the time of interest is after 1900 hours. We only see one event here for sauces. And if we look at the shellbag's output, we see the same story. We only know the last interacted time for sauces because it was the most recently used folder, and we have no times for the folder we're actually interested in, the secret recipes. But we can do better. We can take the preferences keys that we have in the timeline and see what it looks like when we augment it with that. So we have a bunch of extra events here in orange, and we see that we do have that secret recipes event where the properties were modified, showing that the folder was open and closed at that time. And I'll pass it back to Kim for our final conclusions.
Okay, well, I thought you were going to do timeline takeaways, but anyway.
I think we're just a little short on time for that.
Okay, then we're gonna dial it up. Sorry.
We're just gonna skip one.
We're gonna skip one. Okay, main conclusions. So first, just because there's an artifact you've worked with for years does not mean that there isn't more to learn about it. So either things that others in the community have found or things that you might discover yourself. If you've got an idea about a registry artifact that might have some secrets to reveal, then we encourage you to give Nataken a spin. Where do you get it? at the Straws GitHub repo. This QR code will take you right to Nataken, but there are other open source projects up there to check out as well. You can also follow the Straws DFIR Twitter account to get updates about what is up on our GitHub, new blog posts, and other highlights of what the team at Straws is up to. So speaking of, our team also has 2 more presentations at the conference, real-world case studies of Microsoft 365 attacks at 5 p.m. today, and then a deep dive into the Windows Search Index and all the secrets that it can reveal tomorrow at 2:05. So the work we presented today was a continuation of years of work in the community. There is no way to thank everyone, but we have called out here some of the specific folks that we referenced in the talk. And finally, do we have time for questions?